Hello everyone, let's go ahead and get started to this webinar. Welcome. Today's webinar is going to be in coordinates with the Back to Basic blogs that we've been publishing, and it's going to really focus on the latest 3 that were published. Back to Basics on the systematic capability, the architectural constraint, and PFD. So we're going to dive a little bit deeper into all 3 of those categories and talk about them as a whole and what they are together as well today. For those of you that might not know me yet, my name is Lauren Stewart. I'm a CFSE here at Exida. My degree was in mechanical engineering, so I mostly focus on our mechanical customers. A lot of our customers are working designing final elements and then using those final elements. I'm also a teacher at Exida Academy and do a lot of our research initiatives for the company. Just in case you are unfamiliar with Exida as well, we are all about functional safety. So any type of functional safety, alarm management, or cybersecurity, the whole way through the complete supply chain in multiple different industry sectors, we can help you out, whether it's our consultants, our expertise, our tools, our software, our training, our calculations, anything you need. We have experts that can help you out with functional safety, alarm management, and cybersecurity. And no matter where you are, where your devices are coming from, where your devices are going to, where your customers are, we have people close by to help you out. And this map isn't even the most up-to-date. We've opened a couple of different offices since this map, and we are actually looking to open a couple more next year, which we're really excited about. And last note on Exida, and then we'll get into why you're really here. But I always like to mention this to all of my customers. We publish everything we publish our procedures, all of our research, everything we're doing, whether it is through blogs like the Back to Basic blogs, through webinars like these, which are both free on the internet. We have white papers that you can download for free. We have books, we have databases, we have templates, we have all sorts of information to give you a head start in functional safety, alarm management, and cybersecurity. Whatever we're researching, whatever we're looking up, we want to get that information out as quickly as we can, because if we're finding things to make the world a safer place, what good is it holding on to it and keeping it just to us? So we would like to try and get that message out as much as possible. So always check back into our books, our webinars, our white papers to see the latest and greatest research that we've been doing. So let's get to why you're here today, though. And it's, like I said, today we're going to really focus and expand on those last 3 Back to Basics blogs that were posted. The one a couple weeks ago was on systematic capability, then PFD or PFD Average, and architectural constraints being the latest one. We will take a deeper dive into each of those topics and look at how they play a function together as a whole. We're going to look specifically first at systematic capability. We're going to look at what it is, how a product gets a systematic capability, and where you can find this systematic capability at. Then we're going to focus on actually, I think PFD is next. I might have to change this. Next, we're going to focus on probability of failure on demand, or PFD. You might have heard PFH or PFD average. We're going to explain what all it entails. We're going to look at the equation and all of its variables and why it's so important. And then finally, we're going to wrap up with architectural constraints. We'll look at how each are defined, what they actually mean for you, and the different routes approach that the standard talks about. Then we're going to wrap up on how important each of these are in functional safety and in SIF design. and tell you, it's a good thing to be doing all of this, then where it goes and where it comes from. If you have any questions throughout the webinar, I'm not the best at stopping and taking questions throughout. I just kind of get on a roll and keep talking. However, if you have any questions, please put them in the panel, and there's a questions tab on the panel, and you can let me know exactly what your questions are. I'll take some time at the end and make sure to go back and talk about those. So let's go ahead and get started. So there are the three subjects we're covering today: the systematic capability, the architectural constraints, and the PFD average, or probability of failure. They're often grouped together and are either called the three design barriers, or what else are they called? They're called a few different things, but the point is the main functional safety standard, IEC 61508, defines all three and said that each of those three things determines if a product meets a SIL rating or not. The systematic capability of the product itself, the architectural constraints for the element, and the PFD calculation for the entire product. The standard says very clearly throughout IEC 61508 and IEC 61511 that you can't pick and choose which ones you want to comply to. You can't say, oh, I'll look at architectural constraints and PFD average only. Unfortunately, you have to meet all three of these requirements to become compliant in the standards. Like I said, you can't just cherry pick one or two of these requirements, and even if you do them wonderfully, it doesn't matter. You have to meet all three of the requirements to get that SIL rating, or that achieved SIL capability for the product itself. So the first, as I said, they're also thought of as the three design barriers. They can kind of be thought of as barriers, or almost hurdles, that you don't just pick or choose one or two of them. You have to complete each of the three barriers, or the three hurdles, to be SIL compliant. The worst case, or the lowest SIL, is what actually determines the SIL for the product. So if you meet your systematic capability or your PFD average of SIL 3, however your architectural constraints are only a SIL 1, or vice versa, then the entire product is the lowest of that barrier. So that would then be a SIL 2, or whatever the lowest barrier of the product is. So let's start at looking at the first barrier, or that first hurdle that we're talking about, but the systematic capability. So the systematic capability of a product is all about the quality management system. This is where the requirements for that quality management system come into play. The systematic capability is established by having your quality management system audited per all of the requirements of IEC 61508. So if a quality management system meets each of these requirements, then a SIL capability is issued. In each of those SIL capabilities, there's going to be more and more requirements. So if something is SIL 1 rated, it'll have a lot of good requirements in it. However, if it's SIL 2, it will have all the SIL 1 requirements plus all of the new requirements to achieve SIL 2. Same goes for SIL 3 capable. It not only has the SIL 1 requirements, the SIL 2, but also the new SIL 3 capable requirements as well. So the higher the systematic capability for a product is, the more requirements had to be met from their quality management system. This is the information that shows big and bold print on a certificate. The certificate is stating the systematic capability of a product. So if you see something like SIL 3 capable, you now know that SIL 3 capable is talking about the quality or the quality management of that device and how many of those requirements it really did meet compared to other products out there. And I'll show you an example later of what a certificate looks like and where you can find this information exactly on the certificate. So the first barrier is pretty self-explanatory. It doesn't take too much information to get, and there's a lot of requirements for it. However, we can now move on to SIL based on PFD, or probability of failure. This could be, if you're in low demand mode, PFD average, or the average probability of failure on demand, or if you're in high demand mode, this could be considered PFH, but it's still considered the second barrier or the second hurdle. When we talk about the PFD average, and because most of the process industry is going to be in low demand mode of operation, so I'm going to be talking as if we're in low demand mode. But everything's a slightly different if you were in high demand or a dynamic application, and that would be PFH instead. But for the PFD average calculations, it's an extremely important calculation for end users to do. It's a part of engineering and part of one of those 3 design barriers for not only the product, but it is a design barrier also for the end users, and that calculation is a key portion of what they need to do to see if they've met all of their risk requirements for their SIF. It's probably one of the most difficult of the 3 barriers to meet if realistic assumptions are being made and realistic failure rates are being used. There's a lot of information that goes into the PFD average calculation. There are simplified equations which you can use, or more complex equations that don't just have so many assumptions. And we'll take a look at what that equation is and some of the variables that can be used in the upcoming slides. The probability of failure on demand, or PFD, the calculation enables end users to find what their SIF's safety integrity level is. So after completing this calculation, they'll find out what their SIF's PFD average is and find out what SIL level they are actually going to be operating in. So once again, these tables come straight from IEC 61511 and 08, and these tables are going to help end users know exactly what pieces of exactly how safe and how reliable the pieces of equipment they're using are. As I said earlier, there are some simplified equations for PFD average, and there are some more complex equations that take into consideration more variables than assumptions. On one of the main equations that we're using for PFD average has 9 key variables, and it's taking into consideration both things that the end user is in control of and also the manufacturer is in control of. Things like device failure rate, that is going to be provided by the device manufacturer. And things like end of life, mission time, proof test interval, proof test effectiveness, that can all also be suggested by the manufacturer, but what the end user is actually doing and actually participating in is what actually goes into this calculation. So as a device manufacturer, you might not be able to give your customer all of the information in the PFD average calculation. However, you should be able to provide the information such as the systematic capability, the failure rates, and the architectural constraints for your customers to be able to do these equations themselves. So they take those variables that go into the equation, and as you can see, one of the more complex equations is there on the bottom of the screen, put it into that lovely calculation, and then we can then calculate what the average probability of failure on demand is, then the end users will be able to find out what SIL level they are actually running at against. As I said before, there's a lot of variables in the PFD average that are controlled by end users, such as if they're actually proof testing and proof testing on time, if they're following the which proof test procedure, their mission time, all of that. However, you can give them a lot of pieces of the information for them to do this calculation. The third barrier that we're going to be talking about today is architectural constraints. It's commonly referred to as Route 1H or Route 2H. This barrier was set up basically to be a reality check almost, to make sure that there's a minimum hardware redundancy requirements, that people can't just cheat the PFD average calculation with unrealistic numbers and say that they're a SIL 4 with no redundancy. This architectural constraints is kind of that checks and balances of IEC 61508. The architectural constraints are evaluated for each element separately. So you might think of an element as being the final element, so the solenoid, actuator, valve combination together. And as I said before, it was kind of set up to make sure that the PFD average or the PFH calculation isn't overly optimistic and put in fake numbers just to get an overly inflated result. There are two methods to prove your architectural constraints from the standards. You can do that by Route 1H or Route 2H. Each of these routes has a different associated table in the standard to be able to do the calculations against. So the first route, Route 1H, is one that maybe more people are familiar with. Route 1H is sometimes also referred to as a safe failure fraction calculation. It is done by looking at the failure rates of each device, or of the device, and calculating the percentage of safe failures compared to the percentage of dangerous undetected failures. So things that will either be figured out by diagnostics or that would result in a safe failure instead of a dangerous or bad condition. This safe failure fraction was the original method of architectural constraints, and in 2010 they changed the safe failure fraction calculation because people were overinflating it, or they were kind of cheating it a little bit. So instead they welcomed a second option, Route 2H. In changing the Route 1H equation, it made it very difficult for simple mechanical devices, something like a valve or an actuator. It made it very difficult for those devices to meet the safe failure fraction, since they didn't really have many safe failures or those internal diagnostics to help that number. Because of that, a lot of simple mechanical devices were not necessarily passing Route 1H any longer. So they introduced an alternative method in the 2010 version of the standard called Route 2H. And Route 2H is based on more reliability data. We're looking at more proven in use. Is this part been out for a very long time? Is it a ball valve that really hasn't changed in the last 20 years and you really haven't had any issues with it? And we are able to look at all of the requirements of the standard and see if we have a high confidence rating, an over 90% confidence rating in the reliability of that historical data. How we apply 2H in exida, when we get a device, we do an FMEDA, or failure mode effect and diagnostic analysis on this. And we break up the device into each nut, bolt, screw, seal, anything you can imagine, and look how each part could be affected by some sort of stressor. So would this bolt shear, or would it bind? Would this O-ring leak, or could it bind? And then if some sort of stress was applied to it. And then if it does leak or bind, would that encourage a safe or a dangerous condition for the product? So when we're doing that FMEDA process, we also go through each individual component and see if it makes the requirements for 2H. If every single component in the device meets that proven in use or prior use justification requirement, then the entire product is 2H qualified. So we have a massive database of all these components that we've been collecting for over 20 years to analyze the history of each of those components in that exact environment. So as I said, there were tables associated with both 1H and Route 2H. So this is a look at the Route 1H table. So as you can see on the left-hand side, you have the safe failure fraction. So you would do your calculation, and then wherever you fell, that would be your SIL capability along with your hardware fault tolerance. So how to read this table, let me see if I can get a pointer here. Okay, so how to read this table is, say you did a safe failure calculation and it came out to 75%. So you said, great, I'm in this range. So if you calculated you needed a SIL 1 in your risk reduction, or that's how much protection you needed, you can go up here and see your hardware fault tolerance, or what that really means is the redundancy. The hardware fault tolerance or redundancy is 0, meaning you don't need an extra set of equipment to do the same thing. However, if you're at a 75% and you needed to be a SIL 2, they're letting you know that the hardware fault tolerance is 1. What this means is you need an extra set of equipment to do the exact same job. So you might need to be a 1 out of 2 or a 2 out of 3 type redundancy or architecture. However, if you're 75% and you needed to be a SIL 3, this is letting you know you need a redundancy of 2. So that might be a 1 out of 3 device or a 2 out of 4. So that there's an extra 2 pieces of equipment for backup if needed. Different table for 2H. It once again eliminates the safe failure fraction because you don't need this equation any longer. Kind of simplifies things. It just lets you know which SIL you need to be. Say you needed to be that SIL 1. Once again, you don't need any hardware fault tolerance. This time at SIL 2, you don't need any hardware fault tolerance. There's no extra sets of equipment needed. However, once you start getting to your SIL 3 range, there's going to be an extra set of equipment needed. It's going to be, once again, a 1 out of 2, a 2 out of 3 type architecture. If you look back to this table, that's the same as this realm in our table, so they kind of line up together. So now we know all of the 3 barriers. So how does this information get to a product? How does this product get done? Where is this information found? Well, a lot of it happens in a certification process. So in the certification process, when we look at a device, we always start with a kickoff meeting. Then we perform that FMEDA, that failure mode effects and diagnostic analysis of a product. That FMEDA will give us our failure rates for each device individually. So those failure rates not only go into the PFD average portion of the 3 barriers, but it also gives us information if it's going to be 2H or 1H for the architectural constraints of the product. Then we go ahead and do a proven in use analysis. A proven in use analysis, this kind of covers 2 areas as well. This is going to look at your systematic capability of the product to make sure that there weren't any quality mistakes, but this is also going to help with your PFD average of a product. The proven in use analysis looks at both the field failures and the shipments and returns and sees if there's how comparable they are to the predicted failure rates in the FMEDA. If one is way different than the other, we like to investigate and find out why. The next thing we have is our process analysis. Our process analysis is going to be our safety case. We look at all of the requirements in the standard and see how that device or that quality management system meets each of those requirements. This is going to take care of that systematic capability circle for us. Once again, as I mentioned earlier, if you have a SIL 1 product, you're going to have a bunch of requirements. SIL 2, you're going to have all those SIL 1 requirements plus all the SIL 2s. Same with SIL 3 and so on. Next, we have the on-site audit. We go to the manufacturer's facility. We collect some documents, we ask them some questions, we see how the manufacturing processes actually look, go out on the plant floor, and this actually has a little bit of coverage in all three. We look at their manufacturing process, their failure rates, everything in this on-site audit. Then finally, we have a second independent evaluator look over each of these practices and gives it a thumbs up or thumbs down. But once again, they're going to review each one, all three of these variables or all three of these barriers or all three of these bubbles that we look at. At the end of a certification, the result is a certificate. Yay! So at the certificate, it's going to show a lot of really important pieces of information. So the certificate lets you know what SIL level you have for a product. That's talking about the systematic capability. So it's usually big in the front and big bold letters. So your systematic capability is going to show up right there. That talks about the quality management and all of those requirements of the standard. You also have your architectural constraints listed on the certificate as well. It's going to let you know what type of device it is, type A or B, if it's a simple mechanical device, or a more complex element like type B. It's also going to say if it was evaluated per Route 1H or Route 2H, and give you some barriers with that, if there's maybe a redundancy requirement for different SIL levels. And then finally, depending on if it's a device or an element or if it's a complete little loop or not, you might be able to give the PFD average, but chances are it's just going to give you the things you need for the end users to calculate the PFD average. Remember, there's a lot of variables that the manufacturers don't necessarily control. So a lot of the times they give you the failure rates on the back of the certificate, and you can calculate that PFD average on your own. So when you see a certificate like that, it's telling you that it is in complete compliance. It's looking at that systematic capability, it's looking at the probability of failure, and also it's looking at the architectural constraints of the element. So when an end user gets a certificate, it has everything they need to be able to do their calculations and figure out what exactly they need to protect themselves. So SIL, let's take a 180, let's stop where we are and kind of look the other direction. So we know how a SIL is made for a device, what all goes into it, those three barriers on how somebody can achieve that SIL. We know how to read the SIL off of the cert, but how is a SIL used? How do end users actually use that SIL? Why is it important for these three barriers or all of this information to get to your customers? Well, they use it in four major ways. To establish risk reduction requirements. And this is going to be one of those calculations and tables in the standard. They're going to look at how much risk, they can calculate how much risk they currently are standing, and then what their tolerable risk is. The difference will be their risk reduction that they need, which will equate to one of these four SIL levels. It also will let them look at their probabilistic limits for hardware, for random hardware failures. What does that mean? That's going to be calculating the PFD average or the PFH for their entire SIF to guess or kind of predict when those failures are going to occur so they can do proof testing and maintenance before and pull it from end of life before it gets to that point. Next, there are architectural constraints. Once again, this is for the whole SIF. Is there redundancy needed? When we looked at those Route 2H, did it suggest that you needed 1 or 2 extra sets of equipment to do the same job for that sill level? And how that SIF is going to be able to manage that for the entire safety function. And then finally, we have to establish systematic capability. Once again, we're going to be looking at it instead of just for each device, for the entire SIF, so the entire safety system. Do each of those pieces, the logic solver, the sensors, all of the final elements, are all of those systematically capable rated? If you need your entire safety system to be a SIL 3, are each one of those devices SIL 3 rated? Or is one of them a SIL 2 or maybe SIL 0 or not even SIL qualified? Is there some outlier? If there is, that can throw off the entire SIF. So if, once again, it's the lowest denominator, if one of those pieces of equipment is not systematic capable rated, or has a lower one, the entire SIF has tanked. It is a SIL 0 or whatever that lowest is. So those are the 4 main ways that end users use this, these pieces of information, or these 3 barriers that you're going to give them or you're going to present through your certificate. And as I said, they correspond to the tables in IEC 61508. So they not only have their PFD or 61511 as well. They not only have their PFD average tables associated with the safety integrity level, but they also have their risk reduction factor tables associated with them. So they do their calculations and they're able to calculate what they are hoping, the risk reduction they're hoping to achieve, and also what the risk reduction that they're actually achieving. So that's our webinar for today, our webinar on systematic capability, PFD average, and architectural constraints. I'll go ahead and take some time for questions because I did not throughout. And if you have questions later, feel free to email me. And as I said earlier, check out our reference materials. We have great books. We have white papers, webinars, blogs for free that are a lot of really good information. So if you're looking on getting more into functional safety, that's a great place to start. Also, we have some classes and trainings coming up. We have a few coming up soon, but we also have online trainings as well. So if you've really liked this functional safety stuff and you want more of it, feel free to check out our trainings. And we're also going to be at the Rockwell Automation Fair upcoming. So if you're in the area, stop by and see us. We'd love to chat more with you about this. Okay, so let me go ahead and get to the questions now. Okay, we have a question specifically on the Excellentia software, and I'm not an expert on that, so I will, if you email me, I will get that answered for you later. Okay, the next question. Okay, so a question that I'm also often being asked, if IEC 61511 based the hardware fault tolerance requirements on the 2H tables, and the device certifications are now being used based on 2H data, do end users need to have their own proven in use analysis to claim minimum hardware fault tolerance compliance for SIFs using that device? If you are using certified products that are already stating they are 2H compliant, no, you don't need your own database. That is one of the pros about buying a certified device. If you do not buy certified devices and you're trying to prove your 2H compliance on your own, then yes, you will need your own database. And just to let you know, that database is quite large. The amount of information you need is quite extreme to meet it. The reason we were able to put together a database that met the requirements is because we've been collecting the data for the last 20 years. If you want more information on 2H, we have specific blogs and webinars just on 2H. So I suggest, I think they're recorded on our YouTube channel and our website. So I suggest you take a look at one of those webinars, and the whole 30 minutes is just on 2H. Can you develop the aspect of a customer needed to implement SIL 3 using several SIL 2 equipments? Depending on what you're talking about, it depends how this question could go. If they are only SIL 2 capable compliant, they can never go into a SIL 3 loop, no matter how many of them you stick in. Your systematic capability is definitely going to be a limiting factor on this. You can always go back to the device manufacturers and say, I need this to be a SIL 3. And they can easily be reevaluated and to see if they meet the SIL 3 requirements, or you can use different equipment. However, if you need a SIL 3 loop, if your devices are only SIL 2 capable, it doesn't matter how many you put in, it's not going to be enough to get you that third hurdle or that third barrier. The next question, if 2H and 1H shows different SILs, which one shall be considered? That's a great question. You only need to evaluate your product either per route 1H or route 2H. You do not need to evaluate your product per either. However, saying that, the entire safety function or your safety system or your SIF needs to be evaluated on the same one. So your sensors, your final elements, your logic solver either all need to be 1H or all need to be 2H. So it doesn't really, chances are all of your products are not going to meet both. So if you do have a product that meets both 1H and 2H, you're going to have to go with whichever one this system is. Okay, if a device has a systematic capability of SIL 3, but a PFD average gives you SIL 2, what's the overall SIL? This is a great question. Your overall SIL is whatever that least factor is, or the lowest factor, or the lowest common denominator. So if you have those 3 barriers or those 3 hurdles, and each one gives you a SIL 3 except for one of them, maybe that PFD average gives you a SIL 2, that's your limiting factor. Your entire SIL is going to be that SIL 2. So whatever the lowest one, no matter what barrier it is, that is going to be your limiting factor. Is it required to have all three of those elements for safety certification? Yes. So as I said before, think of those as hurdles of a race. You can't just go over one or go over two. You need to complete all three of those hurdles to be in compliance of the standard. If you miss one of them, or if you ignore one of them or don't do one of them, you are not in compliant, or you do not have any SIL rating at all. It's only if you meet all the requirements of all three of those barriers or those circles are you going to actually have a SIL rating or be compliant with the standard. We have a question on trying to figure out if a SIF requires redundant devices. That's going to often, there's a lot of calculations behind that to see if you need redundancies. But the one way of to figure out if you need redundancy is that architectural barrier. That's going to let you know, depending if you do Route 1H or Route 2H, if you're going to need an extra set of redundancy or not. But that's just one of the things that you need to calculate. Juan, if you email me later, I can get you some more information on this, but to figure out redundancy, you need more than just figuring out the hardware fault tolerance on that one table. Okay, and I think, okay, we have some more coming in, hold on. Okay, so we have a question relating the hardware fault tolerance to spurious trip cases. Those are kind of two separate subjects. Yes, if you increase your redundancy, you do have a chance of also increasing your spurious trips. So you should definitely look at your safe failure rate for each device to calculate that spurious trip rate. However, the hardware fault tolerance is going to be independent of your spurious trip rate. It could influence it, but it's kind of two different topics. But if you're adding redundancy, there's a very good chance you're adding to those spurious trip rate. So I always let my customer know, look into your safe failures. Don't just worry about your dangerous failure rate. Also, always look into that safe failure rate as well. Because as much as you don't want a dangerous failure, you don't want to be shut down or lose production loss either. We have a question. We sometimes use reliability data available at plant database. Sometimes it comes out less conservative than global data. Is it acceptable to use that data? It really depends. Depends on how good that data is, where it's been collected, if it's the same, type of information, how deep that reliability data is getting. Are they actually looking at root cause analysis, or is it just scraping the surface? I always tell my customers, look at silsafedata.com. That's going to be I call it a sanity check. It lets you know in what range failure rates should be for each type of device, and you can see if your failure rates for each device are coming into that range. If it's way different than that silsafedata.com, I would, question it. You might have processes and procedures that show you are way above and beyond and better than everybody else. However, is that the reality? If your data is showing it's much better than everybody else in the globe, Is that what you're actually seeing and actually producing, or are you just trying to kind of fool yourself? The next question is, can we calculate the PFD average with the number of failures, of the elements that we have encountered and installed in the company. So you can, that's going to get a little messy. Usually the PFD average is calculated with a failure rate. Some people do calculate a failure rate just by looking at the field returns. However, that's usually a big red flag when I'm looking at data. Depending on what type of device you have, you don't know if you're actually being told if something breaks, how many are coming back to you. What you count as a failure could be totally different than what somebody else counts as a failure. So when we encounter those failure rates, as I said, they're major red flags when we encounter them here at Exida. It, I guess, can be done, but I don't think it's the right thing to do. They can lead to extremely optimistic calculations. We have control valves installed for the last 25 years. How do we derive proven and used data? So that depends on how you've been documenting it in the past. If you have been documenting it in the past, there are programs that can help you do this. There's databases. We have a program called SILSTAT that can keep you, that kind of does that for you. But if you send me an email, I can get back to you later with some specific details. Oh, sorry, that's the Academy email address. Let me get my email address back up. There we go. There's my email address. Sorry about that, guys. The next question is cycle test considered a reliable method, by Exida, a reliable method. It depends on what you're talking about. Cycle testing, if you are in a dynamic or a high demand application, cycle testing can give you a lot of great information about useful life. However, we see probably 90–95% of people are not in high demand or constant or dynamic application. They're not moving every hour. Their valves are going in position and kind of sitting there until they're proof tested, or even just sitting there for years, not moving. Using cycle test to predict failure rates when a device isn't actually cycling and moving is comparing apples to oranges. So if you are in high or continuous demand mode of application, cycle testing can be valuable. However, if you are not, if your valve is not moving every hour, every day, it is not going to be a reliable failure rate justification. It might give you a good mission time or useful life. However, it's not really applicable in low demand cases. I think that's all the questions I had. Like I said, if you have any more, feel free to email me later. Thank you so much for joining me today, and hopefully you enjoyed it. Come back and see our upcoming webinars.